and welcome to Wazimetrics. My name is Looney and I'll be assisting you to get all of your questions through to us. Today we're doing your final exam prep for maths. All you need to do is search us on all the social media platforms, Wazimetrics, as well as hit us up on our WhatsApp line. Don't forget guys, we've got a cool competition going on for you, so do stay tuned to get all of those details. I've got Nicolene, our sign language interpreter with me, as well as our awesome teacher, Nicola. Thank you so much guys, and over to you.
Thank you so much, Looney. And welcome to all the matrics. This is your final exam preparation for Maths Paper 2. Today we're going to hopefully cover some analytical geometry, some trig, and then at the end we're going to try and do some Euclidean geometry. So we've got a lot to get through, so let's get started. Okay, we're going to start with some analytical geometry, and we're told that we have, in the diagram, we have C, which is the center of a circle defined by x squared minus 6x plus y squared minus 4y plus 9 is equal to 0. We can see that's our circle over there with center C. And then we have point T, has the coordinates minus 1y, and it's a point outside the circle. And we have two tangents which are drawn to the circle from T. So there's T over there. And then we have that tangent over there, and we have this tangent over here. So this tangent goes to point A on the circle, and that tangent to point B. Okay, so we're told that STB is a tangent to the circle at B and has the equation y equals minus 2x plus k, whereas TA is a tangent to the circle at A and is parallel to the x-axis. And finally, we're told that BV is a diameter of the circle. So that's this line over here, diameter, which goes through the center. All right, so the first question is we're asked to determine the coordinates of C. So just to remind you, point C is the center of the circle. And we have the equation of the circle. But in order to be able to extract the coordinates of the center and, of course, the radius of the circle, we need to rearrange this by completing the square and getting it in the form of x minus a squared plus y minus b squared is equal to r squared. And when we have it in this form, then the center of the circle is the point with coordinates a, b. All right, so let's do some of that algebraic manipulation. So we have x squared minus 6x. The constant that we need to add to x squared minus 6x is plus 9. To turn it into a trinomial, that's a perfect square. Then we have plus y squared minus 4y. And the constant we need to add to those two terms is plus 4. To turn that into a trinomial, that is a perfect square. I'm now going to put all the constants on the other side. First, I'm going to start by taking this plus 9 to the other side, which becomes minus 9. And then, of course, I'm going to add the plus 9 and the plus 4 that I added to the left-hand side to create those perfect squares. So I'm now going to factorize each of these trinomials. This is going to become x minus 3 squared. This trinomial is going to become y minus 2 squared. And on the right-hand side, this simplifies to 4. And from here, I can now extract the coordinates of that center. So C now has the coordinates 3, 2, which I get from there and there. And although it hasn't asked me for the radius, I can see from here that the radius squared is equal to 4, which means that the radius is equal to 2. Okay, so C has the coordinates 3, 2. All right, let's go to the next question. The next question is determine the equation of BV. All right, so BV is this diameter over here, and we know that it now goes through the center of the circle, which has the coordinates 3, 2. So that's really important. We're going to use what we figured out in part 1 or part A in this question. And so it's going to go, we're going to use each bit of information we get probably in the next question or the next section. Okay, so to find the equation of that line, we need two things. We need the gradient of the line, and we need the coordinates of a point on the line. So we have the coordinates of a point, and that's point C, which obviously lies on the line. how can we get the gradient of the line? If you look carefully, B is obviously the point of intersection between the tangent and this radius over here. And our circle geometry tells us that the tangent is always perpendicular to the radius. And we're also told what the gradient of this straight line is. This line's gradient is -2. So therefore, the gradient of BV is perpendicular to the line SB. So therefore, their gradients, the product of their gradients, must be equal to -1. So the gradient of line BV times -2, which is the gradient of line SB, must be equal to -1. And therefore, we know that the gradient of line BV is equal to 1/2. And always just take a moment to think about whether it makes sense. We expect BV to have a positive gradient, and it does. Okay, so it's 1/2. Now, the last thing we need to do is we need to find the equation of that line. So we're going to use our equation formula. Y minus y1 is equal to m into x minus x1, where m is the gradient and x1, y1 is of the coordinates of a point. So we can now substitute those in. We know that y minus 2, got the 2 from that over there, is equal to 1/2 into x minus 3. I'm just going to neaten that up so that I have y equals. So I'm going to have y is equal to 1/2 x minus 3 over 2 plus 2. And finally, y is equal to 1/2 x plus 1/2. So minus 1.5 plus 2 gives me plus 1/2. Okay, so that is the equation of this line over here, BV. All right, let's move on and see what the next question is. The next question asks us to determine the equation of line TA. Okay, so TA is this line over here. Now, we were told that TA is a tangent, and we were also told that it is parallel to the x-axis, and we really need that information to be able to find the equation of this line. So any line that's parallel to the x-axis is always going to have an equation of form y equals c, where c is the y-intercept, okay, or the point where that line cuts the y-axis. So again, we're coming back to this point C, which has the coordinates 2, 3. And we also know that the radius of the circle is equal to 2. So there's actually quite a few radii drawn here. There's a diameter over there, and there's this radius over here, AC. And we know that that is 2 units. So we are already 2 units up when we get to point C, because we have, we are 3 units up when we get to point C, because we have the y coordinate of 3. And now we go another 2 units up from that, so we're going to be at 5. So therefore, this line cuts the y-axis at 5 units, and we can therefore say that the equation of the line for TA, the equation is therefore y equals 5. Okay. All right, we now have to calculate the length of TB. Okay, so, and we have to give reasons. This is really important. Okay, so TB is that line segment over there. And we can see that it is the length between point T, which is the point outside the circle, and point B, which is where the tangent meets the radius or the diameter. And we know that, of course, this line over here is going to be equal to that line over there. Why? Because the tangents from the same point outside the circle will always be equal to each other. So, can we calculate the length of this line over here? So we know that it is -1, the x-coordinate of this point is -1. And we also know that the x-coordinate of this point is 2. So therefore, we know that the distance between those 2 points over there, -1 to 2, gives 3 units. So if this line TA is equal to 3 units, then this line TB must also be equal to 3 units. So TB is equal to TA, which is equal to 3 units. And our reason is that they are tangents from the same point, that point being point T. Okay. All right, we've got the same diagram. Okay, let's determine the value of K. K is the y-intercept of that line, y equals minus 2x plus k. Okay, so we have the gradient of that line being minus 2, and the value of k is going to be the value of the y-intercept, as I said. Okay, so in order to find that, we need to know the coordinates of another point on that line. And luckily, we do have the coordinates of another point on the line. It's this point T, and we now know that the x-coordinate is minus 1, and the y-coordinate, if you remember, this line is 3 plus 2, which is 5 units up. So therefore, this point has the coordinates minus 1, 5. And I can substitute those two values into this equation to find the value of k. So when x is equal to negative 1, and this is on line S or TB, let's call it TB, on line TB, when x is equal to 1, y is equal to 5. So I'm now going to substitute those into this equation. So therefore, 5 is equal to minus 2 times minus 1 plus k. So we have 5 is equal to minus 2 times minus 1 is 2 plus k. Therefore, k must be equal to 3. Therefore, the equation of this line is y equals minus 2x plus 3. And now we've found that value of k. All right. And the last question is that we need to calculate the value of angle ACB. Okay, so let's go and look at this diagram. Okay, so angle ACB is this angle over here. It's that reflex angle. Okay, well, it's actually an obtuse angle. It's not actually a reflex angle. So how are we going to find the size of that angle over there? Usually, when we're looking at angles in analytical geometry, we're going to be using our gradient formula. And our gradient formula tells us that tan of the angle that a line makes to the x-axis is equal to the gradient of that line. So there's quite a few ways that we could actually probably find that angle. I mean, it would be possible to say, find the size of that angle over there, and then subtract that from 180 degrees to get angle ACB. But a more efficient way to be able to calculate the size of this angle is to look very carefully at this quadrilateral over here. You can see there it is. So it's quadrilateral ATBC. And if we understand our circle geometry, we can see that that is a cyclic quadrilateral. And the reason it is cyclic is because those two angles over there are both equal to 90 degrees. They're both the angle between the tangent and the radius, which means they're both right angles. And of course, when we have a quadrilateral that has an opposite pair of angles being supplementary or adding up to 180 degrees, we know that the quadrilateral is cyclic. And the reason that's useful is because the exterior angle of a cyclic quadrilateral, which is this angle over here, the exterior angle of the cyclic quadrilateral is always equal to the opposite interior angle. So in other words, if we can find the size of this angle over here, angle STA, then we have effectively found the size of this angle over here, which is angle ACB. And luckily, this angle happens to lie between the positive x-axis, or I should say a line that is parallel to the positive x-axis, and this line over here. Okay, and I know that the gradient is equal to -2. So I'm going to call this angle theta over here, and I'm now going to use this little formula which tells me about the relationship between the gradient of the line and the angle of inclination of that line. So I'm going to say that tan of theta is equal to -2. And therefore, that angle theta is equal to the inverse tan of -2. Right, time for the calculator. Pull that out. Okay, so we're going to find inverse tan of -2 and close our bracket. And that gives us an angle of minus 63.43 degrees. So obviously we don't want the negative version, we want the positive version. So we're going to add 180 degrees to that. And we get the angle as being 116.6 degrees. Okay, so therefore it is equal to 116.6 degrees. And if this angle theta is equal to 116.6 degrees, then this angle over here must also be equal to 116.6 degrees. And again, your reason would be that we have the exterior angle of a cyclic quadrilateral. Okay, so that's it for this segment. In the next segment, we'll be looking at some trig, which is one of my absolute favorites, very exciting. And otherwise, I'll hand back to Looney.
Thank you, Nicola. Guys, let's take a quick break and we'll see you shortly after this.